All right, welcome to video 3. This is the official, I guess, recipe for applying implicit differentiation whenever we have an equation that's not explicitly solved for one of the variables. So when I don't see a y equals everything in terms of x, or x equals everything in terms of y, or whatever other variable, whenever I don't have an isolated variable, I can use implicit differentiation to find the derivative of y with respect to x. So, 4 steps. Number 1, take the derivative of both sides of the equation. So we're going to do step number 1 right now, and we're going to use example 2 to find the derivative, differentiate both sides of the equation with respect to x. So I go to my equation. In example 2, my equation is here. Notice there are two sides. I have the left side and I have the right side. So I'm going to take the derivative of, so step 1, take the derivative of the left side of y squared plus 2xy minus x to the third. And then we're going to take the derivative of the right side. I'm writing d over dx to say we're going to take the derivative of 4 with respect to x. I'm taking the derivative of all of this in red with respect to x. So I'm using this notation to remind me that my variable is x. I'm zooming in a little bit. We can find the derivative of 4 fairly quickly, right? The derivative of a constant is just 0. But when I try to find the derivative of this whole set of terms, I notice that there are 3 terms that I have to deal with. I have to find the derivative of y squared. I have to find the derivative of 2xy. And I have to find the derivative of x to the third. And I'm supposed to add the first 2 derivatives and then subtract the third one. So, taking the derivative of y squared with respect to x, that would be 2y times, I'm treating this as an inside function, so times the derivative of the inside, which is dy dx. Plus, I'm trying to find the derivative of 2xy. The problem is I have x's and y's. So I actually have to do a product rule. I'm going to take the derivative of 2x, which is 2, times the second function, y, plus the derivative of the second function, 1, times dy dx, times the derivative of the first, which is 2x. All of this comes from the middle term, 2xy, since I was multiplying 2 separate functions, 2x and y, which I'm treating as a function of x. I had to do the product rule. Minus, take the derivative of x to the third, but I'm taking it with respect to x, so therefore this derivative is just 3x squared. We're lucky in that in this problem, we're adding this bracketed part. So if I'm adding, I can just erase those. If I wasn't adding, if I was subtracting, then I would need to subtract the first term and subtract the second term. I would basically need to distribute the subtraction there. All right, so when I get to this point, I have finished step number 1. But I need you to notice we have 1, 2, 3, 4 terms on the left side and 1 term on the right side. Terms are separated by pluses and minuses. So therefore, I have 4 separate terms. That's what we need to notice, because in the next part, we're going to need to move some of those terms around. So I go to step number 2. Step number 2 says, collect all the terms that have a dy dx. I'm going to do this in this color. Collect all terms that have a dy dx on the left side of the equation and all others on the right side. So remember, we said we had 4 terms. The ones that have dy dx, like this one and this one, they're going to stay on the left side. So this stays here, plus 1 dy dx. But all the other terms, let me get rid of this bracket. All the other terms, we are going to move to the other side of the equation. So that means that this 2y, we're going to subtract to the other side. And this minus 3x squared, which doesn't have a dy dx, we're going to add to the other side. So you can write it in this format, or you can write them, you can switch them and write 3x squared minus 2y. But these are the ones that need to go to the other side because they do not have a dy dx. So let me change this to this color. Minus 2y plus 3x squared. Great. I've separated my terms into the ones that have a dy dx on the left side, the ones that don't have a dy dx on the right side. Next step. Factor a dy dx out of the left side of the equation. Factor out a dy dx. Well, yes, if the two terms on the left side have a dy dx, I can factor out dy dx, and I'm left with 2y plus 1. And on the other side, I'm left with negative 2y plus 3x squared. Again, you can also write this right side as 3x squared minus 2y. So far, so good. I think we're good. All right. And then we go to the last step. The last step is solve for dy dx by dividing. So I'm going to do step number 4 here. We're going to solve for dy dx by dividing both sides by the expression in the parentheses. So if I divide this side by 2y plus 1, and if I divide this side by 2y plus 1, then dy dx will equal negative 2y plus 3x squared all over 2y plus 1. Here I have found my derivative formula, my derivative equation that's going to give me the slope of the tangent line for this graph. Now, be aware that this formula now is in terms of x's and y's. So before, whenever we wanted to find the derivative, we had to plug in an x value to find the actual slope at a point. Here, we're going to have to plug in an x value and a y value to figure out the slope of the tangent line at a specific point. Here are the 4 steps we need. Step 1, implicitly take the derivative of both sides. Step 2, move anything that doesn't have a dy dx to the right side, anything that does have a dy dx to the left side. Step 3, factor out a dy dx. Step 4, divide both sides by whatever you're left multiplying by dy dx, and you have your derivative equation. This is how we use implicit differentiation to find the dy dx formula. Some people would call it the y prime formula. This is the derivative equation. We'll come back in the next video and we'll do example number 3.